Okay. Chapter 18. So do you guys want to go over like anything from last session first, or just move on to chapter 18? Because we finished chapter 17 last week, and I plan to finish chapter 18 this week, and the last week tomorrow, next week we just go over final review, like from all old material to new material. We could just jump straight into chapter 18 today. Yeah. Okay. So chapter 18 is all about the alpha carbon chapter, where let's say we have a carbonyl like this, right? This carbonyl carbon here is not the alpha carbon. That's the carbonyl carbon. The alpha carbon is 1 carbon away from the carbonyl carbon. The beta carbon is 2 carbons away. Gamma is 3 carbons away. Delta 4, and then epsilon 5, right? But this chapter, we are going to focus on the alpha carbon. Now, the last chapter was on aldehydes and ketones, where let's say we have an aldehyde here compared to a ketone here. Let's look at the alpha hydrogen. Do you guys remember which alpha hydrogen is more acidic? The one on the aldehyde or the one on the ketone? Right, on the aldehyde. Because let's say we use some kind of base, like ethoxide. When we deprotonate the alpha hydrogen of the aldehyde and ketone, we are going to get this conjugate base here. Right? Conjugate base. Conjugate base. To determine which is more acidic, we see which conjugate base is more stable. We see that both of these conjugate bases can do resonance with that carbonyl there. So the amount of resonance is the same. So the next thing we look for is induction. We know this is an R group that donates electrons inductively, like that, right? This hydrogen here is not an R group, so it will not donate any electrons at all. Because this R group is donating electrons towards this negative charge, that's going to be less stable because negative charges repel each other, right? So this is a less stable conjugate base. This is a more stable conjugate base. So on the exam, if he asks you which one has a lower pKa and he writes out like the name of a aldehyde compared to a ketone, the one with the lower pKa is the aldehyde one, the one that's more acidic, right? Where pKa and acidity are like inversely related. The more acidic the molecule is, the lower pKa it has. So let me write that down. The aldehyde here has a lower pKa. Ketone has a higher pKa. Right? Okay. Yeah. So now let's revisit keto-enol tautomerization. This is a reversible reaction where if we have an enol like this, that will tautomerize into a carbonyl like that, right? In most cases, this carbonyl form is more stable and major than this enol form. The case where the enol form is more favored than the carbonyl form is when we have an aromatic ring. So let's say we have this enol here compared to this carbonyl here. We know that this left structure is aromatic and the right structure is non-aromatic, right? Where this part of the structure is the enol and this part is the carbonyl. So when your structure has a lot of conjugation resonance with the enol form, that's when the enol form is the major form over the carbonyl form. When the structure has no conjugation or no resonance with the enol, then the carbonyl form is the major stable form. Okay. And this tautomerization step here can happen in acidic conditions and basic conditions. Let's go over the acidic conditions first, where we have an enol and we are in base, like let's say H2SO4 and water. The first step here, we could reform the carbonyl right away and use that alpha carbon to attack. Right. Before we use that attack, I'm just going to draw out the resin structure out to show why that alpha carbon is nucleophilic. Right. This right here is the resonance structure of that structure there, where we see that there is a full negative charge on that alpha carbon, making that alpha carbon the nucleophile. Where this nucleophile here can then attack an electrophile or attack an acid, acidic hydrogen, like that, right? Which gives us the structure. And the last step here is just to neutralize and deprotonate that carbonyl carbon, oxygen, to give us our carbonyl form. So this is tautomerization mechanism in acidic conditions. Right? In yeah.
And like the bond, the hydrogen bond attached to the oxygen, and that step happens very quickly. Usually, the step where the negative charge on the carbon attacks the hydrogen.
Oh, like when this goes here and then you can just draw the arrow straight from there.
Yeah.
Yeah, that is the more common way to draw it in the mechanism. I just drew out this resin structure to explain why that carbon there attacks the hydrogen. But in tests and papers or the textbook, they usually draw it in this way, where they just reform the carbonyl right away, and they know that this is the nucleophilic atom, which that is just going to attack the hydrogen, kick out the conjugate base right away, instead of drawing out this resin structure there, right? Because these two are the exact same structures, they're just different forms.
The bond with the double bond attack like the no, like just go down.
Oh.
They just drew.
Oh, right.
Like that,
Uh-huh.
the
Oh, this.
how they go up too, or
Right. So this double bond here, we'll have to move somewhere, because when we try to make a double bond between this carbon and oxygen, that's going to break the octet rule. This carbon is going to have 5 bonds, 1, 2, 3, 4, 5. So to conserve the octet rule, this double bond has to move somewhere.
oh, so it moves to the hydrogen.
Yeah, so it goes to the hydrogen. That's where the carbon hydrogen bond comes from that alkene bond right there. Right. Right. So let me make that more clear by highlighting that alkene bond, which is this bond right here. It made that bond between that carbon and hydrogen. And then the last step here is just to neutralize that oxygen by deprotonating it, like that. Okay, so that was acidic conditions. Let's look at tautomerization in basic conditions, which is the faster mechanism. And I'm going to draw out the alcohol like that, showing out the bond between the oxygen and hydrogen. So let's say we have NaOH, a strong base. That hydroxide ion is going to deprotonate the alcohol, giving that alcohol, oh, that oxygen a negative charge right there. Right. And then from here, we created water. When this hydroxide ion grabs a hydrogen, that becomes water, which is going to be our proton source when we reform the carbonyl and then use this alpha carbon to grab the hydrogen and kick out the hydroxide ion. Right. And then the basic catalyst gets reformed, hydroxide ion. Okay. Okay, let's go on to the next reaction, which is going to be alpha halogenation. So let's say we have this ketone with an alpha carbon here. And this specifically is a methyl ketone, because one of the R groups of the ketone is a methyl group with 3 alpha hydrogens, right? There's going to be 2 conditions that this reacts in: acidic conditions and basic conditions. Let's say we have some kind of X2, like CO2, Br2, I2, and in acidic conditions like H3O plus or H2SO4 or some carboxylic acid, any strong acid, right? And the solvent is going to be water. This reaction here only does mono-halogenation, where let's say I'm going to label the X as green. We're only going to add 1 X to that alpha carbon there, substituting only 1 alpha hydrogen. There's still going to be 2 alpha hydrogens on that carbon right there. If we were to do this in basic conditions, like X2, XS, and let's say NaOH, this is going to substitute all of the alpha hydrogens into halogens like that. Right? So acidic conditions, only mono-halogenation, where we only add 1 halogen to the alpha carbon. Right? In basic conditions, this is poly-α-halogenation, where we add multiple halogens onto the alpha carbon. Okay, let's go over the mechanism of the acidic conditions and then the basic conditions afterwards. Right. Let's say we have this ketone with that alpha carbon, and we put that under acid, like H2SO4. The first step of the mechanism is that that carbonyl oxygen gets protonated by the strong acid. Right. Once we have done that, this alpha hydrogen here is more acidic now, where the conjugate base of the acid that we used to protonate the carbonyl oxygen is going to grab that alpha hydrogen and form this enol here. This bond between carbon and hydrogen is going to make a double bond there and then kick out that leaving group there. So think of this as like an E2-like reaction, where the base grabs the hydrogen, makes a double bond there, and then kicks out a leaving group. But that leaving group doesn't fully leave because that's a double bond. We're going to create that double bond. We're going to form a single bond from that double bond there, which also neutralizes the positive charge oxygen, giving us this enol here, right? Where, do you guys remember which atom of this enol is nucleophilic when we draw out the resin structure? Yep, the alpha carbon here, right? So that alpha carbon is going to be the one that attacks the halogen. Let's say we draw the X2 out. We're going to reform that carbonyl. That alpha carbon is going to attack the X and kick out the other X. Right? That's going to give us this carbonyl, where that oxygen still has a hydrogen. So a positive charge is there. And then the X that is attached to that alpha carbon now. Right? Where the last step here is just to deprotonate the carbonyl oxygen to make it neutral. And we stop here at the mono-halogenated alpha carbon. We only add one halogen in the acidic conditions, right? The reason why we cannot do this reaction again is because if we protonate this carbonyl oxygen, right, this alpha hydrogen here is less acidic now. Because, oh, actually, no. This is actually more acidic because, wait, let me just draw for you. So let's protonate that carbonyl oxygen. Protonate that carbonyl oxygen. This alpha hydrogen here is more acidic because the halogen here makes it more positive. So let's say we do deprotonate that and make the enol again. Which is the alcohol next to the alkene right there, right? But now this alpha carbon is less nucleophilic because if we draw in the resonance structure and give that carbon a negative charge, that negative charge right here, is it going to be more or less stable with the halogen on nearby it now? Right, it's going to be more stable because this halogen here, think of it as an electron withdrawn group, which withdraws those electrons, making it more delocalized and more stable. Since this negative charge there is more stable than the negative charge on the first enol form, is it going to be more or less reactive if it's more stable? Less reactive, right? So that's why we can't add another halogen onto the acidic conditions. We only stop at one halogen in acidic conditions, right? Because this nucleophile here is more stable, meaning that it is less reactive or less nucleophilic, will not attack another X2. So your final answer will stop at this point here in acidic conditions. Stop at the mono-alpha halogenated product in acidic conditions. Right. Okay, so now let's do the basic conditions mechanism where we do poly-halogenation at the alpha carbon. Let's bring in that same ketone. And this time we are in basic conditions. So let's say we have that strong base hydroxide ion. What that would do is form an enolate ion right away, right? By deprotonating that hydrogen, forming an alkene there and popping this double bond onto that oxygen there, which will give that oxygen a negative charge and an alkene there. Right? The next step is that this alpha carbon is going to attack the X2. As we reform the carbonyl, this carbon here is going to have a negative charge in the resonance structure, which is going to attack that X and then kick out the other X. Okay. That gives us this halogenated alpha carbon at right, the alpha carbon there. The next step here is to now deprotonate the second alpha hydrogen using the strong base that we are given to form another enolate ion. Right. Once we do that, we get this enolate ion here. Okay, so now the difference between this enolate ion in basic conditions and the enol in acidic conditions here is that this alpha carbon is more reactive, more nucleophilic than that enol there, right? Because the positive charge here is making that negative charge more stable. But this is not a positive charge. This is a negative charge. And if this is a negative charge, will that make this alpha carbon more or less nucleophilic if there's a negative charge there? More nucleophilic, right? Which is why that alpha carbon here is able to attack another X2 in basic conditions, not the acidic conditions, because that acidic conditions there makes it more stable and less reactive. Basic conditions makes it less stable, more reactive. So we can attack another X2 here. Right. So let's bring in another X2. Reform that carbonyl, attack the X, kick out the other X. Now we have a dihalogenated alpha carbon. We keep going until we substitute all of the alpha hydrogens into the X. So we repeat this process one more time. The strong base comes in, deprotonates that alpha hydrogen, form the enolate ion. And then that alpha carbon of the enolate ion will attack another X2. Right? So we're going to reform the carbonyl, use that alpha carbon to attack the X, kick out the other X. That gives us this poly-α-halogenated ketone here. Okay. But it doesn't stop here for iodine. Wait, let me see what's going on here. Alpha-halogenation mechanisms. I see. Okay, yeah. So in basic conditions here, what we just formed is going to be the intermediate. Because think of this whole thing as a good leaving group. And do you guys remember what makes a group a good leaving group? Like when a leaving group leaves, what charge does it leave with? Right, so it's going to leave with a negative charge, right? Because let's look at an example of this right here. Let's say we have this SN2 reaction and we put NaCN. We know this Br is a good leaving group. When we use the CN nucleophile to attack this electrophilic carbon and kick out that leaving group, what charge would the bromine have when it leaves? Negative charge, right? So a good leaving group will be able to handle a negative charge better. Or well, a good leaving group will be able to stabilize the negative charge. Bromine is a good leaving group because it is a really electronegative atom, and electronegative atoms are able to hold negative charge as well. Bad leaving groups are like R groups and hydrogens because these groups here do not hold negative charge as well, right? So this is a good leaving group because imagine that there's going to be a negative charge at that carbon right there. That negative charge at this carbon is going to be stable because of these electronegative atoms here. These electronegative atoms here are going to stabilize that negative charge of that carbon when it leaves, which is why this is a whole good leaving group here. Right. So the next step here is that we're going to bring in the hydroxide base. attack that carbon, pop the double bond onto the oxygen to get this structure here. Now, once we have this structure here, we do have a good leaving group, which is this CX3 here. We're going to reform the carbonyl and then kick out that CX3 leaving group, which gives us this carboxylic acid here, right? But when the CX3 leaves, it leaves with a negative charge, which is a base. The very last step here is that that base is going to deprotonate this acidic carboxylic acid to give us our final answer, the carboxylate ion here, plus the CX3 that's protonated and neutral here, right? So let me update the chart here from the alpha halogenation. It doesn't stop here. That is the intermediate with the CX3. Right? So let me draw those intermediate brackets. It goes further to make the carboxylate. Right there. Plus CHX3. Right? The reason why it doesn't stop here is because since we are in acidic conditions, basic conditions, the base will attack the carbon, pop the double bond to the oxygen to give that negative charge, and then that negative charge will come back down, kick out that CX3 group, which becomes that right there. And then we get a carboxylic acid, which will get deprotonated by that negative charge, CX3. So this is what we get, a carboxylate from basic conditions. Okay. Yeah.
You might be getting into this, but what if, like, let's say you had like a more substituted side versus like a less substituted side of like alpha hydrogen, like a secondary carbon versus like a primary carbon, like a pure preference.
Right. So, let's see here. Let's see. Something like this. Let's say we have a ketone, asymmetrical ketone.
Like
oh, right. Something like this versus like that, or like this.
Yeah.
Let's see. For basic conditions, it would prefer the less substituted side, because let's look at the poly-halogenated alpha carbon here versus if we halogenated the left side here, right? And let's say this was the leaving group with a negative charge on that carbon versus if this was the leaving group with a negative charge on that carbon there. We see that the negative charge on this carbon is more stable than the negative charge on this carbon. So this makes it the better leaving group. So we would prefer the left side because we get to add more excess there that would stabilize the negative charge. Right. So it would prefer the left side. Stable, better leaving group. More stable with the negative charge. With negative charge, better leaving group. This one is less stable with the negative charge, worse leaving group. So it prefers to attack the less subside. Right. So I say X2. Okay. Ooh, okay. Yeah. Yeah. So to recap the mechanism for basic conditions, what happens is that the strong base will deprotonate the acidic alpha hydrogen to form the enolate ion. From this enolate ion here, the nucleophile is not that oxygen minus. The oxygen minus does not attack the X. The alpha carbon is a nucleophile because if we draw in the resin structure, we will see that the negative charge Right, so here's a question. Where is the negative charge more stable at? At the oxygen or the carbon? Yeah, the oxygen. So since the negative charge is more stable at the oxygen, that is less reactive. And if the negative charge is less stable at the carbon, that's more reactive, which is why the alpha carbon here is the nucleophile, the one that attacks. The X, and take out the other X, we get that mono-halogenated alpha carbon there. We have two more alpha hydrogens, so we're going to repeat this whole process 2 more times until we get to this point here, right? Where we substitute all of the alpha hydrogens into halogens. Once we get that, we don't stop here because we're still in basic conditions and we have a good leaving group now, CX3. That base is just going to attack the carbon-carbon, pop the double bond onto the oxygen to give this tetrahedral intermediate. This O minus here is going to come back down to reform the carbonyl, carbon double bond oxygen, and then kick out a leaving group here, right? When that happens, that's the leaving group that left. And this is the carboxylic acid that we formed. This carbonyl oxygen came from that oxygen there. This OH came from that OH there that attacked that carbon, right? We know this is a carboxylic acid, which is acidic. So we're going to use that base that left to deprotonate that carboxylic acid to form the final answer carboxylate. Okay. If you did acid workup, like at the very end, like H plus or H2SO4, H2O plus, that's just going to protonate the carboxylate back into the carboxylic acid. But if we are just in basic conditions, it's not the carboxylate because basic conditions have negative charges, acidic conditions has positive charges. Yeah.
What are like some synthetic uses for this, like the carboxylate ion?
Right, so this I've mostly seen for lab questions, like the iodoform test, right, which test for if you have a methyl ketone or not. I rarely see this on synthesis on the lecture exams. This is more for lab. Yeah. Right. The next thing we're about to go over is more for lecture, like the Aldol, Markov, Robinson annulation. Those are the big ones. Right. That's more for synthesis because you got to know like which bond was formed to make a disconnection between them. Yeah. Yeah.
Basically, on the ones that said poly-alkylation, if there's both on both sides, there's both alpha hydrogens, which just put BRs on all of them.
Yeah, we just substitute the BRs or whatever halogen you use, Cl's iodine, with the alpha hydrogens that you have. This is usually used for methyl ketones where we have 3 alpha hydrogens, which is why in this case we substituted all these 3 alpha hydrogens with these 3 halogens here.
Okay, so basically, if there's, because you know how in acetones, there both sides have alpha hydrogens.
Yeah.
There'd be like in total 6 bromines if you did bromation with basic.
Yeah, I think let's see. Let's see if that were to happen. Let's see. X. We know this is a leaving group, so let's say a base comes in, attacks, pops it up there. O minus, OH. X. Next, reform the carbonyl, kick out that leaving group. And then we know that we're going to get that carboxylic acid, where this CX3 minus comes in, grabs that hydrogen, forms the carboxylate. Right. Let's see. Can this attack? No. Right. At this point here, the hydroxide ion cannot attack this carbonyl-carbon anymore. That's because this carbonyl-carbon is more stable now from the negative charge oxygen here. This is able to do resonance, making it more stable. If it's more stable, it's less reactive right there. So we won't be able to pick that out there. Wait, let's see. Let me look at the mechanism if we could add halogens on the other side as well. Let's see. X. Yep. Once we get to this point, let's imagine this was a methyl group here. Oh, okay, yeah. So that won't happen. You only add it at one side because imagine there are alpha hydrogens here, right? The hydroxide ion will not deprotonate that alpha hydrogen and make the enolate ion there. What it would do instead is attack that carbon-carbon, pop out there, to create this structure, come back down and take out the good pair. Right. So that's why we only get it at one alpha carbon.
Okay.
Yeah.
Thank you.
Let's see. Yeah, so this cannot happen in the first place. Okay. Okay. Any questions on the alpha halogenation reaction? It's more used for lab to test for metal ketones, right? Okay, let's now move on to the first major reaction of chapter 18, Aldol condensation. Okay. So some basic information about this reaction. Your nucleophile is going to be an enolate ion. Your electrophile is going to be a carbonyl. Either, not just any carbonyl, it can't be a carboxylic acid, ester, amide. It has to be either an aldehyde or a ketone. Right.
Use formaldehyde.
Yeah, you can use formaldehyde as well. Formaldehyde will also be used as an electrophile, right? Okay. And the product that you form is going to be an aldol, right? But under heat, that aldol is going to make an alpha beta unsaturated carbonyl. And I'll show you what that is specifically. Okay. Okay, let's look at an example here. And there's going to be three types of aldols that you guys could do. There's going to be self-aldol versus mixed aldol versus intramolecular aldol. Right? Okay. Let's look at the self-aldol first. Let's say we have this aldehyde here with 3 alpha hydrogens. Right. Oh, another thing about this reaction is that this always happens in basic conditions. So the reagent is always a base, strong base. Right. The reason why the reagent is always a strong base is because we want to form an enolate ion here from this carbonyl. How can we form an enolate ion here, like from this carbonyl here? Right. What an enolate ion is a deprotonated enol, because an enol would be this alkene next to an alcohol. This is not an enol, but this is an enolate. When you see enolate, then there's a negative charge on that oxygen right there. To form this enolate from this carbonyl, we have to deprotonate the alpha hydrogen. And then to deprotonate the alpha hydrogen, we need a strong base, which is why in this reaction always occurs in basic conditions. It never occurs in acidic conditions, because acidic conditions can never form this enolate ion here. Right. So let's say we use like NaOH as the base. That hydroxide ion is going to deprotonate that alpha hydrogen and then form that enolate ion there. Right. Now we have our nucleophile. Right. That's the first step of the mechanism. You generate your enolate ion. Your nucleophile. Generate enolate nucleophile. Since we are doing a self-aldol condensation, let's bring in another aldehyde. Right? Because this aldehyde here in solution is in excess. There's a lot of them around. So what will happen is that this carbonyl is going to get reformed, and this alpha carbon here is going to be the starred carbon, the nucleophile carbon. This carbonyl carbon of the aldehyde is the dot carbon, the electrophilic carbon. The nucleophile will attack the electrophile and then pop this double bond onto the oxygen there. Right. When we do that, we're going to connect the star and dot atoms now. This is the star atom. This is the new bond that was formed between the star and dot atom. This dot atom here, it was attached to a double bond O, but we popped that double bond onto the oxygen, making that into a single bond O minus, negative charge. That dot atom is also attached to a methyl group, which I'm going to draw that methyl group like that. It's also attached to a hydrogen, but I'm going to leave that hydrogen as invisible, but the hydrogen is still there. Like this hydrogen of the dot atom is like, let's say right there, but it's invisible. Right? Okay. So we formed water in the first step here when we deprotonated the alpha hydrogen, which is going to be our proton source to protonate the O minus charge and create our aldol. Right? This right here is our aldol. You could think of it as aldehyde near alcohol. Right? Aldol. Aldol. Right? But this is the important thing here. The alcohol has to be beta to the carbonyl carbon of the aldehyde or ketone. If it's alpha or gamma or delta, this wouldn't be considered an aldol. To be considered an aldol, the alcohol has to be beta to the carbonyl. Okay. You would stop here if you are in low temp. Right? Because this reaction that we just did is aldol condensation. If let's say you are in heat, high temperature, you are going to do aldol dehydration. Like that. Okay. So let's say we are in high temperature, high heat. The reaction can occur again by deprotonating the alpha hydrogen and forming the enolate ion again. Okay. We are going to form this enolate ion and alcohol there. Okay, now this is the last step of the aldol dehydration here. We're going to reform that carbonyl, carbon double bond oxygen. This double bond here is going to shift to make a double bond here. And then this is the new thing here. We usually said that the alcohol is a bad leaving group, but in this example, that alcohol is going to be able to leave because of the high temperature here. We add enough energy for that leaving group to leave. We are also in basic conditions where there are other hydroxide ions around to support that hydroxide ion to leave. But if this like heat wasn't there and we're not in high temperature, this leaving group would not be able to leave. Like if we were in room temperature, this leaving group would not leave. Right? And that gives us this final answer here. Right? Which this is called an alpha beta unsaturated carbonyl. Where there is an unsaturation between the alpha and beta carbon, which is that double bond right there. from the carbonyl. And this hydroxide ion here came from that leaving group that left. This leaving group was able to leave because we have heat. This is the dehydration step. We dehydrated this water or alcohol there, hydroxide there. Okay, so now let's move on to mixed aldol. Before we go over that, let's go over predicted product example problems where I'm going to show you guys how to predict the product without drawing this whole mechanism to save time on the exam, right? Let's say we have that original structure that I had at the beginning, that aldehyde, and we put that under NaOH, water, and heat. We said the product was this alpha beta unsaturated carbonyl there, right? So to predict the product quickly, find your alpha carbon from the carbonyl, which is this carbon here. We know that alpha carbon is going to be our nucleophilic carbon because once we deprotonate it, we form the enolate ion, which makes this carbon here have a negative charge. So that alpha carbon there is this alpha carbon right here, right? This bond there attached to this starred atom was the electrophile, right? So let's make a cut between the star and dot atom or the alpha and beta bond, double bond, right? Once you make a cut there, you could go backwards, right? Where this star was that aldehyde, and then this dot here was the electrophile. And what did we say? What was the electrophile for Aldol reactions? Like what got attacked from the enolate ion here? What does the enolate ion attack for Aldol? Yeah, carbonyl group, right? Where that dot carbon that I just dotted came from the carbonyl group here, which has a methyl group and an invisible hydrogen. But I'm going to draw that invisible hydrogen out like that, right? But you notice how at that dot carbon in the product, there's no oxygen there? Where did that oxygen go in the mechanism? Like this oxygen here, go. Imagine the key is there. Okay. Dehydrated, right? Because in the first part of the mechanism, we formed that aldol, the alcohol beta. Like at the first part of the mechanism here, we had an alcohol there, right? When this like star atom attacks this dot atom, it pops the one to the oxygen to create an OH there. But because we have heat, that OH group left. Okay. So that's how you can tell like what's your nucleophile and electrophile here for the synthesis. So if he gives you this in the synthesis product problem, just make the cut between the alpha and beta carbon. The one with the carbonyl is your nucleophile. The one with no carbonyl is the electrophile that used to have the carbonyl, but that carbonyl got kicked out by dehydration. Yeah.
Like you know how we're adding another carbonyl into it? Like you know how in the reagents it just says NaOH, like how would
Yeah.
how did we come up with adding that extra aldehyde group?
But this extra aldehyde group is the same aldehyde group as this right here,
Okay.
where this is just in excess. Like we have a lot of these
Okay.
in the solution. Where the base here, whenever you see strong base, you always look for your most acidic hydrogen to deprotonate, which is the alpha hydrogen here. Once we do that, we form an enolate ion there where we know there's going to be a negative charge on that alpha carbon. Once we have formed our nucleophile, we have to look for something to attack at our electrophile. The something else to attack is another version of itself. So that's why this is self-aldol. It attacks another version of itself.
Okay.
Which will eventually turn into this after dehydration. Yeah. So let's look at one more example here. Let's say I give you an alpha beta unsaturated carbonyl, and you guys predict what's the nucleophile and what's the electrophile. Let's say. Okay. Yeah. Try predicting the carbonyl in basic conditions that would create this alpha beta unsaturated carbonyl from an Aldol reaction. Yeah. Oh, yeah. Oh yeah, my original one broke this. I was writing so much, like 3 years, and then the film like broke off, and I think it's so. But this is like I need to get rid of one. So what you did, you cut that alpha beta on so great. When we do that, you know how this is right there. Oh, right here. Then this is our electrophile here, but the nucleophile. We need that. We use it right now in our atom. Is that maybe yes, might have another. Like that. Now, not that with the nucleophile, that means it's electrophile. Okay. Yeah. This would not be self at all because it doesn't have any plastic. Yeah, it's a mix. Oh, yeah. I tried to make this self, but then this is I was just like going to the next thing we'll talk about. Oh, okay. So this one is but this is right. Oh, because I say one of so it's the answer yeah, the answer is a mixed one, which is right in the case. I wanted to make this self, but then I forgot to add a method somewhere, right? Which is gonna be I need a method there, right there, yeah. There you go. Or to be this self. Yeah, okay. So the way I think I just make the process right there. Right there, right. Where that right there. Is that starting right there? Yeah. Okay. Yeah. Okay. So this product here will actually come from two different things. The nucleophile is not the same as the electrophile, right? But if I add a methyl group there, right? Then this would be a self aldol. Okay. So what did you guys try for this problem here? Like, what did you guys do first? So what we have to do first is find the alpha and beta carbon to the carbonyl. This is the alpha carbon. This is the beta carbon. Then make the cut between the alpha and beta carbon, right? The one with the carbonyl, the alpha carbon is always a nucleophile. So let's draw that nucleophile out here. Right. Which is that nucleophilic carbon there. Now, the one with the beta carbon, just put an oxygen right there to get your electrophile. Oh, another thing, let me put that note down. Alpha carbon is the nucleophile, beta carbon is the electrophile. That's why I starred the alpha carbon because I know that's the nucleophile. I dot the beta carbon because I know that that's the electrophile. So when I draw out that electrophile, I get this here, right? Where this beta carbon here is this carbon there with the carbonyl. Before, I gave this product with no methyl group. If there was no methyl group here, this would be an aldehyde because that would just be a hydrogen, which would make this a hydrogen. And this aldehyde here is not this ketone here. That's going to be a mixed aldol, where the nucleophile is different than the electrophile. Okay. Yeah.
The star, like the nucleophile on the left side,
Right.
is there supposed to be a negative charge at the position of the star?
Yes, there is supposed to be a negative charge here at the star from the basic conditions we're in, because this aldol condensation here or reaction always happens in basic conditions. The strong base is going to deprotonate the alpha hydrogen here and give that carbon a negative charge. Yeah.
Well, you can do aldol condensation with ketones.
Let's see. Ketones. Aldol condensation with ketones. Some kind of carbon. Let's see. Maybe the NaOH here is not a strong enough base to deprotonate the ketone alpha carbon. So we would have to use a stronger base instead of NaOH here. But if we use NaOH, then it won't work on ketones. Right. Yeah.
If you remove the methyl of the beta carbon,
Uh-huh.
will the second aldol have a hydrogen?
Yeah. Uh-huh. If that methyl group wasn't there, then this second one here would be a hydrogen like that, which makes this an aldehyde.
Oh,
right. But this structure here can never be the nucleophile because the nucleophile always has an alpha hydrogen. This carbonyl carbon here has no alpha hydrogen. This alpha carbon here has no hydrogens at all. And this is not an alpha carbon.
so this is a mixed aldol reaction.
Yeah, so this is a mixed aldol reaction, right? Where from this right here, you can't use NaOH, strong base, because you know how we said a ketone is less acidic than aldehyde? The NaOH is not a strong enough base to deprotonate that alpha hydrogen. So let me write that down. This is a ketone. Alpha hydrogen is not acidic enough for the base sodium hydroxide or hydroxide ion to deprotonate. You would need a stronger base like NaNH2 or N-butyllithium, but NaOH is not strong enough to deprotonate the ketone alpha hydrogen, right? So aldol usually happens in aldehydes with sodium hydroxide. Okay, now let's go on to the mixed one here. Mixed aldol condensation. Let's say we have two different aldehydes with two different R groups, this aldehyde and this aldehyde here. And we use NaOH, water, and this time 0 degrees Celsius. If I have 0 degrees Celsius, what would be my product? Like no high temperature. Would we stop at the aldol or go all the way to the alpha beta unsaturated carbonyl? Aldol, right? Because we don't have high temperature to make that alcohol leave. We stop at that alcohol product next to beta to the aldehyde, right? In this case here, we are going to look for the alpha carbon, which is this alpha carbon and this alpha carbon here. We have two different nucleophiles. right? Let's say this is nucleophile A, and this is structure B right here. We also have two different electrophiles. Because for aldol, the nucleophile is always the alpha carbon of the aldehyde. The electrophile is always the carbonyl carbon of the aldehyde. Right? So in this case, we're going to have four different products. Let's say we have the alpha carbon of A be the nucleophile, right? And let's say it attacks itself, self-aldol, AA. Alpha carbon of A attacks the carbonyl carbon of A. To predict the product, this is what I do here. I know that this is my starred atom, which is the star atom of A, which is also attached to a methyl group like that. I'm going to make that new bond between the star and dot atom of A, which is attached to an OH and an ethyl group there. Right. So I got this aldol product by making this alpha carbon of A, the nucleophile. So that's the star atom there. And I'm just going to attack another version of itself, which is that dot carbon here. This is new bond between the star and dot carbon when it gets attacked. This star atom is attached to a methyl group. This dot atom is attached to an OH and an ethyl group. It's also attached to the hydrogen, but I left that hydrogen as invisible here, right? And we have to stop at this aldol product because we are in 0 degrees Celsius. We don't have high enough heat to make a double bond there between the alpha and beta carbon. Right? Now, the other product would be, let's say, we use that same nucleophile A, but this time we attack the electrophile B. So this is going to be AB product now. So let's use that same nucleophile with that same star with its methyl group. I'm going to draw out that new bond, and I'm going to color code that blue to show that that's the new bond that gets formed. This is the dot atom, but now this dot atom is now pink because this is the electrophile of B. Right? What is attached to the pink dot atom here when I try to predict the product here? What do I have to include? What do I have to include in that pink dot atom? Yep, an alcohol, which comes from this carbonyl oxygen, and yeah, and a methyl group here. That's the difference between this product and this product here, right? We don't have to draw out that hydrogen because that hydrogen is invisible. If I use this B as my electrophile, that's attached to a methyl, which is this methyl. If I use this A as my electrophile, that's this A electrophile with its ethyl group. So that's the difference between them. Okay. We get two more products here. Now, let's use B as the nucleophile and B as the electrophile. BB. Star, which is attached to a methyl. New bond between star and dot, which we said was attached to an alcohol and a methyl. So that's the third one. The last and final one, fourth one, BA, where the nucleophile is B, the electrophile is A. Wait, so that dot is now red because it is the electrophile of A, which has an alcohol and not a methyl group, but an ethyl group.
You draw an extra methyl for BB.
Oh, extra methyl group for BB. Oh, I did. Yeah. There's no methyl group there, right? Because if I use B as my nucleophile, right? This atom here is my nucleophile, that star atom there. Which is this star atom here? That star atom does not have methyl group at all attached to it. Yeah.
Is the reactivity of A or B like nucleophile or electrophile different because like A has more alkyl groups, or like it has alcohol versus methyl?
The reactivity would not change that much, so you get a mix of this in like pretty major amounts. But what do you think is going to be the more acidic one, A or B? The alpha B. B, because this B alpha hydrogen here only has one R group. For A, the alpha hydrogen here has two R groups, making it less positive. We want the hydrogen to be more positive, to be more acidic, right? But
You mean the alpha hydrogen or the alpha?
alpha hydrogen, right? Alpha hydrogen. The reason why there's no R group on the star atom here is because there's no like R group on that alpha carbon there. Whereas there's a methyl group on that red star atom because that methyl group is this methyl group here on that red star atom. Yeah. So these are 4 different products here. Okay. Yeah.
So we need to put this in the exam, right? It would be like how much
Different products.
different products are
Mhm.
You have to just draw it out how much alpha hydrogen there are.
You could draw it out, or you could like say, this nucleophile can attack itself, that's one product, or the other product, which is 2 products. Or you could say this nucleophile attacks itself, which is the 3rd product, or attacks the other thing, which is 4 products. And then from there, you don't have to drop like the whole product. If he just asks you like, how many products, and then there's multiple choice like 1, 2, 3, 4, you could just like think about how many there is, and then circle 4, right? Without drawing the things. But if it helps you like predict how many there are, you can draw it out as well. So let me give you an example here and ask you how many products will be formed from this here. Okay. Given these 2 aldehydes and basic conditions with heat, how many products will form here? Yeah. Yes. Hmm. Okay. See. Which atom can be our nucleophile here in this reaction? Yeah, the second one here, because that alpha carbon has an alpha hydrogen to deprotonate it from the enolate ion. This first one here, that alpha carbon has no alpha hydrogen, right? No alpha hydrogen, we can't make that the enolate ion. We can't deprotonate that. So this forces this carbonyl of the aldehyde to be the electrophile, and this alpha carbon to be the nucleophile. Oh dang. I could see another product being formed here, right? The first one would be like this being the nucleophile and it attacks this one. The second one would be this nucleophile attacking itself for self-aldol, right? So let's try predicting that. Let's draw the uh nucleophile first. New bond between the star and dot. That dot, I'm going to draw the intermediate first because we have heat. It's attached to this tert-butyl here as the first one. The second one is if it attacks itself. Star, new bond between the star and dot, which is attached to an OH and a methyl group, because this could be the electrophile as well, right? But these are the intermediates because we are in heat, right? So what would the final product look like here? Yeah, that new bond there is a double bond and we get rid of that alcohol. Nice. Yeah. Heat. And what's your favorite one product? Let's see. Hmm. Yes, that's gonna go over the intramolecular reaction, but the intermolecular ones, it's hard to favor one reaction over the other. So we got like two of these in like pretty major amounts. But once we get to the intramolecular reactions, you're gonna favor the intramolecular reaction over the intermolecular reaction. Mm. Yeah, no problem. Yeah. Okay. So now let's go over oh wait, let's go back to this this note here. Right. I've seen some examples where the ketone here can get deprotonated. So this could be the nucleophile as well, right? So let's just erase this note. Right. This one here. Right. Because the alpha hydrogens of the ketone can still get deprotonated to be our nucleophile here. Right. Okay, now let's go over intramolecular aldol. Let's say we have this structure here. That, and we have NaOH, water, and heat. Okay. Which atom would be our nucleophile and which atom would be our electrophile here? Oh, the nucleophile is oxygen or carbon? Oh, right. So for aldol condensation, the nucleophile is going to be the alpha carbon of the enolate. So it cannot be the oxygen. It has to be the alpha carbon of a carbonyl, right?
Be the one on the far right.
Yeah, it would be the one on the far right. The alpha carbon of this carbonyl here would be nucleophile. The electrophile would be the carbonyl carbon of the left side, right? When that happens, we are going to make a 1, 2, 3, 4, 5-membered ring. Because for aldol, the nucleophile is an alpha carbon of an enolate. The electrophile is a carbonyl carbon of an aldehyde or ketone.
Wait, so the nucleophile is the carbon because of that.
Yeah, because of the resonance structure, right? Let me draw out the mechanism where this alpha hydrogen here will get deprotonated by the strong base we have to form this enolate structure here. That's the first step of this mechanism. Generate the enolate ion. Which gives this enolate structure here. But that O minus there is not the nucleophile because when we draw the resonance structure, we see that the negative charge on the carbon is less stable than the negative charge on the oxygen, which makes this carbon here more reactive, more nucleophilic than this oxygen negative charge. So now we could use this negative charge carbon to attack the carbonyl on the left side, right? Since the nucleophile is on the same molecule as the electrophile, this is an intramolecular reaction where we're going to form a 1, 2, 3, 4, 5-membered ring. Right. So let's draw that. The benzene stays the same. O minus. Let's say this is the star. This is the dot. This is the star. This is the dot. 1, 2, 3, 4, 5. 5-membered ring right there. Where atom 5 has a single bond O minus now. Atom 2 has a carbonyl. Right. Nice. Where I'm going to draw out the new bond that gets formed as blue. Right. So this is the new bond that gets formed right there between 1 and 5, between the star and dot atom right there. We're going to protonate that O minus using the water that we formed here to get this aldol. Okay. But if we are in heat, we cannot stop here, right? We are going to deprotonate the alpha hydrogen again, form the enolate ion. This is in heat. O minus. And then from this point, we reform the carbonyl, shift the double bond here, and then kick out that hydroxy group to get this alpha beta unsaturated carbonyl there, right? And in intramolecular reactions, we always form a ring, which is this ring right here. Yeah. So in this case, we saw that the nucleophile came from a ketone, not an aldehyde, which is favored because this intramolecular reaction allows it to happen. Intramolecular reactions are one of the fastest reactions alongside with acid-base reactions. So those are the top two classes reactions, acid-base and intramolecular reactions.
Does it matter where you start your 1 to 5? Because I start my 1 at the carbon,
Oh, yeah. It doesn't matter. It just helps you like keep track of where your atoms are here and what's attached to it. You could number it 1, 2, 3, 4, 5 left to right instead. Or you could say A, B, C, D, E, or that way, or A, B, C, D, E this way. Yeah. But make sure it's consistent, like when you close the ring. Like you have to make it stay as is, like where the atoms are. Like don't switch up the numbers once you set it. Okay. So those were the three scenarios of Aldol. We did self-Aldol, which attacks itself. Mixed Aldol, where there are like different nucleophiles, different electrophiles that will give you different products. And then intramolecular Aldol, which it attacks itself to form a ring. Those are the three Aldol scenarios, three Aldol cases. Okay, let's do micro addition. So to summarize this reaction, the nucleophile here is also going to be an enolate ion. The electrophile here is going to be an alpha, beta, unsaturated carbonyl. The reagent, right, you need is always going to be in basic conditions. Because we need basic conditions to form that enolate ion, to deprotonate the alpha hydrogen and form the enolate ion. The product that you're going to form for micro addition is a 1,5 dicarbonyl. So before we go over that reaction, let's look at an alpha beta unsaturated carbonyl. Okay. I'm gonna number these atoms 1, 2, 3, 4. Do you guys know which atom is gonna be the most electrophilic atom here? Which atom gets attacked by a nucleophile, like an enolate ion, for example? Yeah, so it looks like that case because we're used to seeing the carbonyl-carbon always being attacked, right? But in this case, the most electrophilic atom is that beta carbon right there, right? This is going to be electrophilic because of this right here, resonance. When we draw out the resonance structure of this alpha beta carbonyl carbon, we get this resonance structure where we see a full-on positive charge on that beta carbon, right? That would be nucleophilic if the carbonyl wasn't nearby, right? But because the carbonyl is nearby and it can do resonance, that gives this beta carbon a full positive charge, which makes it the electrophile. Yeah.
1,4 dicarbonyl or 1,5?
For the product, it's going to make a 1,5 dicarbonyl, 1,5 dicarbonyl, right? Because when we see at the product, you start your number 1 at 1 carbonyl carbon, and then you end your 5th carbon at the other carbonyl carbon, right? So if the alkene was here alone and there's no carbonyl nearby, then this could be nucleophilic, which would attack like an HX or X2, the alkene midterm 1 chapter, right? But because there's a carbonyl allylic to it, we can draw it in resonance to get this structure here, where we see a positive charge on that beta carbon, which makes this beta carbon the electrophile, right? So whenever you see this alpha beta unsaturated carbonyl, this carbon here is always the electrophile. That's an important concept. Okay, so now let's do the reaction here. Let's say we have this aldehyde plus this. A shorter way to say alpha beta unsaturated carbonyl is enone. That's just a shorter way to say it. You could think of it as an alkene next to a ketone, right? So we're going to draw in that enone. Use a strong base NaOH, water. The first step here is to look for the most acidic hydrogen in basic conditions. The most acidic hydrogen is this alpha hydrogen here. So we're going to bring in a hydroxide ion, deprotonate that alpha hydrogen, generate the enolate ion. Okay. Based on these structures here, which one's by star or nucleophile? Which one's by dot or electrophile? Let's look at this one here. Which atom would be the nucleophile atom here? Yep, the alpha carbon. Mm. Um, what uh, what just happened? Why? Okay, there we go. So we're gonna start this alpha carbon. Looking at this structure here, which one is my electrophilic atom? Yeah, the beta carbon, which is this carbon here. So we attack this carbon here. Don't attack this carbon, which we're used to attacking. This is the electrophilic carbon here, right? Where we're gonna reform that carbonyl, use that star alpha carbon to attack this dot beta carbon, shift the double bond here, pop the double bond onto the oxygen there. Right? When that happens, we get this structure here. Star that, new bond between star and dot. Attach what is attached to the dot. Just that. O minus here. Now from here, this is an enolate ion, which is just going to tautomerize into the carbonyl. By reforming that carbonyl, using this alpha carbon to get protonated by water to get our final answer here. Which is a 1, 2, 3, 4, 5. 1,5 dicarbonyl. Right? Two carbonyls that have a 1,5 relationship with each other. Right? So to summarize this micro addition, the nucleophile is the enolate ion. The electrophile is the beta carbon of the enol or alpha beta unsaturated carbonyl. The product is a 1,5 dicarbonyl in basic conditions. Ooh, okay. Okay. Any questions on this micro addition reaction? For micro addition, see, 1,5 dicarbonyl. 1, 2, 3, 4, 5. Yes, 1,5 dicarbonyl. Yeah. Right. But then from this 1,5 dicarbonyl here, we could do other reactions on it. We could do intramolecular aldol condensation from this point if we have a longer chain, which leads to the Robinson annulation reaction. But micro addition is just part of that, which will get this 1,5 dicarbonyl intermediate, and then we could like do intramolecular aldol to get to the Robinson annulation product. But micro addition by itself will always form this 1,5 dicarbonyl here. Right. That's micro addition. Where this thing here, the enone or the alpha beta unsaturated carbonyl, is called the microacceptor. It's just another name for the electrophile or the alpha beta unsaturated carbonyl. Right? And this is the microdonor, which donates electrons. Okay. Yeah.
Will like a clear indicator that it's a micro addition be if there's an enone present?
Yeah, if you see an enone, and an enolate ion that could get formed, then that's a clear indicator of microaddition, right? The similarity between microaddition and aldol condensation or dehydration is that the nucleophile is an enolate ion. The difference in aldol condensation and microaddition is the electrophile. The electrophile for aldol is a carbonyl, like the carbonyl carbon of an aldehyde or ketone. The electrophile of a microaddition is the beta carbon of a enone. Yeah, that's the difference between aldol and Michael. Yeah.
When we just think about it, it should just be like alpha, beta, alpha, whenever it connects fully, like ABA.
Oh, like to disconnect this 1,5 product to predict the reactants?
Yeah.
Yeah, so let's see. Let's say this was your alpha and this is your beta. You could make that disconnection between the alpha and beta to predict your reactants, right? Once you make that disconnection there, this is your nucleophile. This is your electrophile where there was a double bond right there. Nice, nice, yeah. That's good thinking for synthesis because that's going backwards, retrosynthesis. Yeah. Right. Okay. Robinson annulation. This will combine Michael addition and intramolecular aldol condensation. Okay, let's see. And then we'll leave the rest of chapter 18 for tomorrow. Yeah. After we do the Robinson annulation, we're just going to do practice problems on Aldol, Michael, and Robinson and summarize like make a table on like the differences between them. Robinson annulation. The first thing that happens in Robinson annulation is a Michael addition. The second thing that happens is an intramolecular aldol dehydration or condensation. It depends on if you have a high temperature or not. Let's say condensation or dehydration. Or dehydration. Condensation if you have a low temp, no heat. Dehydration if you have heat. Okay. So let's say we have this structure and this structure in basic conditions, NaOH and water. Which atom here would be our nucleophile and which atom would be our electrophile? On the left, right here, right? And which atom on the left? Like, would it be this atom or this atom here? Yeah, the top one, because this one has alpha hydrogens, which we can deprotonate to form the enolate ion. This one here has no alpha hydrogens. We cannot deprotonate that to form the enolate ion there. For this one here, the electrophile is the beta carbon, right? Not the carbonyl carbon. That's for aldol. But for Michael, it's the beta carbon of the enone here, right? So let's do this whole mechanism. Deprotonate that acidic alpha hydrogen, form the enolate ion. Star the nucleophile, dot the electrophile. Reform the carbonyl. Alpha carbon attacks the beta carbon. Like alpha carbon of the enolate attacks the beta carbon of the enone. Shift the double bond to make a double bond there, and then pop the double bond to the oxygen. Make the new connection. Star. New bond between the star and dot. This dot is attached to single bond, double bond, O minus. And then from this enolate here, we are going to tautomerize by reforming that carbonyl And that alpha carbon of that enolate is going to get protonated by water. I'm going to color code the new bonds. So then I can explain how we can make the cuts to go back to the reactants, given the product for synthesis. Right, where this micro addition here created a 1, 2, 3, 4, 5, 1,5 dicarbonyl. That's the first step of Robinson, micro addition to form your 1,5 dicarbonyl there. Right. Now, the next step of Robinson annulation is an intramolecular aldol condensation. For intramolecular aldol condensation, what atom would be our nucleophile and what atom would be our electrophile? This is tricky because you have to find out which atom can form a more stable ring, because we don't want to form a 4-membered ring. That's going to be way too unstable. We want to form either a 5 or 6-membered ring for aldol.
Is the carbonyl in the ring gonna be the electrophile?
Mm-hmm. Yeah, the carbon in the ring is the electrophile, and then we have two options for the nucleophile: this atom or that atom there. Yeah, the bottom one, because the bottom one here would create a 6-membered ring. The one on the top would create a 4-membered ring. We don't want that, so we choose this alpha carbon here. Nice. So let's deprotonate that alpha carbon to generate the enolate. Right, where we know that alpha carbon of the enolate is the nucleophile, the carbonyl of the other ketone or carbonyl is the electrophile. We're going to reform the carbonyl, use that alpha carbon of the enolate to attack that electrophilic carbonyl carbon, pop the double bond onto the oxygen to form a 1, 2, 3, 4, 5, 6-membered ring. So let's draw that 6-membered ring here. Right, where this is 1, 2, 3, 4, 5, 6. And let me color code the new bonds that was formed. This was, let's say, blue, and let's say this is purple. That. Okay. Where at carbon 2 is our carbonyl there that got reformed. And there's a new bond between 1 and 6, or the star and dot atom now, which is the purple bond. Now, for the last step for aldol, condensation, protonate the O- to create the OH. Okay. Once we have this, we stop here if we have no high heat. But if we have heat, we're gonna deprotonate the alpha hydrogen again to generate the enolate ion. And then from that enolate ion, we reform the carbonyl, shift the double bond to make that double bond there, and then kick out the alcohol to get our enone. Here, which the product here is another enone. An alpha beta unsaturated carbonyl, right? Cyclic. So this is a cyclic alpha beta unsaturated carbonyl because it is in a ring. Yeah, so that's the final answer for Robinson annulation after micro addition and intramolecular aldol dehydration. This can show up on synthesis where he gives you this as the product, and then you have to predict like what reactant it came from. To do that, right? Let's say that he gives you this as a product. Let's make the disconnections now. We know the last step was an intramolecular aldol. So first, locate your alpha and beta carbons from the carbonyl, or locate your alpha beta unsaturation bond right there. Make that disconnection between the alpha and beta carbon. Which atom is the nucleophile and which atom is the electrophile? Like the alpha carbon or the beta carbon? Like which one would be the nucleophile? Alpha or beta? Alpha, right. Because the one with the carbonyl is the nucleophile. So when we go backwards, let's make that cut. That makes the beta carbon the electrophile, like that. Right? So this is after the cut right here, where this was the alpha nucleophile, this was the beta electrophile there, right? That's the first cut you make. Now, once you get that, right, we know the first reaction of Robertson annulation was microaddition. And for microaddition, what is the electrophile name? Yeah, the enone, right? So we have to figure out which part made our enone. Let's look at this carbonyl here and say that that alpha carbon there was the nucleophile and this carbon here was the electrophile. When we make a cut there, imagine there was a double bond there before. This part here is our enone there, right? So when we made that disconnection, we are going to get this starting material here, that carbonyl and this enone here. Right. Okay. Any questions on this Robinson annulation reaction here? Okay. Let's do another example where we have to go backwards and find the enone and
So typically how these types of
carbonyl.
reactions are.
For synthesis, right? Like for synthesis, he might give you this cyclic enone, and then you have to predict the reactants that come from it, which is going to be another enone and a carbonyl, like that, right? Okay, so let's say we have this as the product. Here, okay. And let's say, okay, yeah, let's say we have this, yeah, this as the Robertson annulation product. Predict the carbonyl that made the enolate nucleophile and the enone that is the electrophile here. There's two disconnections you make. The first disconnection is to find out where the 1,5-dicarbonyl is. The second disconnection is to find out where your enone is.
Oh, yeah. Also, are like these compounds used in synthesis of Aldol?
Like this,
I guess in general, like the products from these, like, are they like useful in synthesis? Or is this like maybe an end?
yeah, this would most likely be the endpoint here. Right. A cyclic, especially if it's cyclic, like the cyclic enone here, that's probably going to be the endpoint of a Robinson annulation product. But if you have not a cyclic enone, right, that could be your electrophile on the arrow for my microaddition. Like if you have a carbonyl and alpha to that is the enolate nucleophile, you could bring in an enone that's not cyclic, like a smaller enone, that would give a 1,5 dicarbonyl for synthesis. Okay, so what did you guys try first? How did you guys make the first disconnection to, yeah.
I'm spinning the double bond,
Mhm.
find the other positions relative.
Right. And then which one would be your nucleophile and which one would be your electrophile here? If we make that first disconnection, would your nucleophile be the alpha carbon or the beta carbon? Yeah, the alpha carbon, which is that methyl group there. And since the beta carbon is the electrophile, we have to keep that carbonyl there on that beta carbon. Right. This disconnection gives our 1,5 dicarbonyl. 1, 2, 3, 4, 5. That's the first disconnection. Now, the second disconnection will allow us to find our enone. And which bond are you going to disconnect to find your enolate nucleophile and your enone electrophile? Which bond are you disconnecting here? Wait, let me make it easier by saying 1, 2, 3, 4, 5. Between what bonds, between what atoms are you going to cut the bond? Yeah, 2 and 3. That's the bond that we're looking for. Which this part is going to be the enone, and that left side is the enolate. Right. So given these reagents here, this would be your Robertson annulation reagents, which first does a microaddition and then an intramolecular Aldol condensation to get this cyclic enone. So Robertson annulation basically combines everything we went over today, the Aldol and Michael, but specifically the intramolecular Aldol for Robertson. Yeah.
Is a way to think about it just like analysis, like the first step?
Almost a half analysis, where when we cut the double bond in half, only one side gets a carbonyl. For analysis, this side would also get the carbonyl as well.
Okay.
Right? So half of it, analysis, the other half, no analysis. Right. But the important thing here is that we form a 1,5 dicarbonyl when we make that first cut. Okay, so let's do some practice problems on this and then finish chapter 18 tomorrow. Oh, no, this is this is the last one, last worksheet. Okay, let's do the weird ones, the weird looking ones. Okay. Oh wait, no, they give you the product for that. Let's do B, part B. Yeah, part B is probably the weirdest one here. Everything else is more followable. Yeah, intramolecular aldol reaction.
Is it gonna be like?
Uh-huh. This is great. So for these types of problems here, look at your reactant and reagents, and then determine what reaction it gives you. Like, is it going to be an aldol? And if so, which kind? Self, mixed, or intramolecular? Is it going to be Michael, or is it going to be Robinson annulation? We know it's not going to be Michael or Robinson annulation because we don't have an enone anywhere. But we do have two carbonyls where we know for aldol, the nucleophile is an enolate ion and the electrophile is another carbonyl. And we have heat as well as the big indicator for aldol dehydration. Right. So let's do this for intramolecular aldol dehydration. Since this is a symmetrical carbonyl, right? Let's say this carbon here is the nucleophile and this carbon here is the electrophile. Right. Let me get more space. I'm going to draw out the whole mechanism. Well, let me copy paste. Okay. So let's say this alpha carbon gets deprotonated by the strong base hydroxide ion, form the enolate nucleophile here. We know this is going to be the nucleophile star. This is the electrophile dot. When we reform the carbonyl, that nucleophile star is going to attack that dot, pop the double bond to the oxygen. Since this is intramolecular, I recommend numbering from the attacking atom to the atom being attacked. So this is going to be our number 1 atom. Go all the way until the atom that gets attacked, which is this atom here, which stops at 5, which is going to show that we are going to make a 5-membered ring. So it also might be helpful to number these atoms here because we're going to make a bond between 1 and 5, which makes another ring on the left side. Let's say this is 1, 2, 3, 4, 5, 6, 7. 7-membered ring on the left side. So let's draw that out really quick. Let's first draw the 5-membered ring, which is easier to draw. And let's say this is 1, 2, 3, 4, 5. The star was on 1, the dot was on 5. That's the new bond between the 1 and 5 atom there. Right? And then let's draw that other ring in. 2, 3, 4, 5. 5. 1, 2, 3, 4. 2, 6, 7. Which is this 1, 2, 3, 4, 5, 6, 7 bond there. Right? Where at carbon 6 that I labeled as pink here has the carbonyl bond there when we reform that carbonyl there. Right? And this dot carbon here will have the O minus here. Right? Does this like point make sense? Like how I got to that point right there? Right. Now for aldol condensation, we are just going to protonate that O minus to get the aldol here. OH and then carbonyl here. Right? Which is the answer for the first part with no heat, the 0 degrees Celsius one. That's the answer. Here, we stop there. But if we have heat, what is going to happen next if we have heat? Yeah, form an alkene between these carbons here and get rid of the alcohol, right? Where if we want to draw the mechanism, is that alpha carbon there gets deprotonated to generate the enolate ion. It forms here. Yeah, that's the most stable alkene, right? You could say that this is also the most stable alkene as well, because it could do resonance with that carbonyl, but it specifically forms here because it has a leaving group to kick out, which is the OH. It doesn't form here because there's no leaving group here to kick out.
Oh, is it also because it's such a substitute?
Oh, right, yeah. This is also tetrasubstituted here. Right. But if this was also tetrasubstituted like that, it will still be this one because there's a leaving group to kick out when we form the double bond. If we form a double bond here, there's nothing to kick out, which breaks the oxide rule, which is not good. Okay. Nice. Enolate. Reform the carbonyl, shift the double bond there, kick out that alcohol to get the enone. Here, with this leaving group. Final answer. Wait, so this is just a weird intramolecular aldol condensation here. Dehydration. This first part here is aldol condensation. The last part with T is aldol dehydration, dehydrating that hydroxide. Okay. You guys can try, let's say, we did aldol. Let's try Michael. Let's try this Michael here. Part. Let's do E, the more confusing one, the weird looking one. Let's do E. Oh wait, actually no, time's up. Oh shoot, I just realized it's 7:30. Do you guys want to go over this really quickly? Part D for Michael. Okay, let's do that. Okay. So I'm just gonna talk through this. For Michael, the nucleophile is this enolate here that gets formed when we deprotonate that alpha carbon. The electrophile is not this carbonyl carbon, but this beta carbon of the enone. So when we reform that carbonyl, this star alpha carbon attacks that beta carbon of the enone, shift the double bond there, pop the double bond onto that oxygen, and we make that 1,5 dicarbonyl by connecting the star and dot, which gets that carbonyl, star, new bond between star and dot. That dot is attached to a single bond, double bond, O minus. That's the R group decoration. And then from here, we reform the carbonyl and tautomerize it by protonating that alpha carbon to get this 1,5 dicarbonyl here. Right. Right. So this dot carbon here is also attached to this benzene ring here. Right. So we also have to include that benzene ring on that dot right here. Right. Don't forget that decoration, that extra group there, which is attached to that dot right there. Right. So everything here is now good. Right. When we have a benzene here, dot there, and then benzene here. Right. So this here is a microproduct because it is a 1,5 dicarbonyl. Yes. Yeah, that benzene is that benzene there attached to the dot. Yeah, nice. Okay. Any questions? Okay.